Hello and welcome back. In the past few lectures, we've been talking about uniform probability spaces where all outcomes are equally likely, and the fact that everything has the same probability makes it very easy for us to calculate the probability of outcomes and of events. And what we'd like to do is, in this lecture, is consider a couple of games of chance and popular games and see if we can calculate different probabilities that come up. So let's start with the game of dominoes, where we have tiles, and each tile consists of two parts, as we see here, separated by a line. And in each part, we have a number of dots, and the number of dots ranges from 0, as we have here, to 6, as we have here. Okay, and the order of the two parts doesn't matter because the difference between 3, 6 and 6, 3 is just rotating the tiles, so these are the same. So we just care about the numbers that we have on one side, and the other just the set of numbers. Okay, so if we're going to pick one of those tiles at random, then the set of possible outcomes is just the set of tiles, which we're going to list here. So there are two types of tiles. There are tiles where the numbers of both sides are the same. For example, here 4, 4, and that's the collection of tiles 0, 0, 1, 1, 2, 2, up to 6, 6. And then there are the tiles where the numbers on both sides, on the two sides, are different. For example, 2, 5 or 3, 6. And they start from 0, 1, 0, 2, and so on for 5, 4, and then 5, 6. Okay. So if we're going to pick one of those tiles at random, then each tile is going to be equally likely. So this sample space is going to be equiprobable. And to calculate the probability of outcomes and events, we just need to see how many possible tiles there are. Or in other words, what is the size of this sample space. So the size of omega is the number of tiles here. And it's fairly easy to see that the number of tiles of the same values, for example, 0, 0 up to 6, 6, that means just picking one number from 0 to 6. And there are 7 such numbers. 0, 1, 2, up to 6. And we need to pick one number, so that's 7, choose 1 tiles or 7 that have the same value. And then for the tiles that have different values, there are 7 possibilities, and we need to pick 2, so that's 7, choose 2. Now 7, choose 1 is 7, and 7, choose 2 is 7 times 6 over 2, which is 21. So the total number is going to be 28. So we have a total of 28 tiles. And with that, we can calculate the probability of any event. Now, there's also a different way of getting to this number of tiles, 28. So we're going to see it. So this is just a different way of looking at things. We can consider the maximum value on a tile. For example, here the maximum value is 5. Here the maximum value is 4. Here the maximum value is 6. And count how many different tiles are there with any given maximum value. So how many tiles are there whose maximum value is 0? There's only one such tile, 0, 0, so there's one tile. How many tiles have a maximum value of 1? That's 2, because these tiles are going to be either 0, 1 or 1, 1. So there are 2 tiles whose maximum value is 1. So that number is 2. And how many tiles have a maximum value of 2? That's 0, 2, 1, 2, and 2, and 2, 2. So there are 3, and so on, up to how many tiles have maximum value of 6. That's the tiles 0, 6, 1, 6, 2, 6, up to 6, 6. So there are 7 of those. So when we want to calculate the total number of tiles, we can just add the total number of tiles that have maximum value 0 plus number of tiles that have maximum value 1, and so on up to 6. And that number is going to be just 1 plus 2 plus 3 all the way up to 7. Okay, and this is just the arithmetic series. So the number is the number of elements here, which is 7, times the average number here, which is 1 plus 7 over 2, or 8 over 2, which is 4. So 7 times 4 is 28, gives us, again, the same number of tiles. All right. So once we have this number of tiles, let's calculate a few probabilities. So first of all, if we look at specific outcome, what is the probability that if we pick a tile, we get the tile 0, 0? Well, it's the same as the probability that we get the tile 1, 2, or any other tile. And each of those has, for example, 0, 0. It's one tile out of 28 possibilities. So the probability is 1 over the size of the support set or the sample set, which is 28. So it's 1 over 28. We can also consider some events. What is the probability that if we pick a tile, then 6 will be one of the numbers on the tile? For example, 2, 6, or 4, 5, 6, and so on. Well, we need to see how many different tiles have 6 on them. And that number we actually calculated at the end of the previous slide is the tiles that this tiles 0, 6, 1, 6, and so on up to 6, 6. There are 7 such tiles, and we have a total of 28 possibilities. And we pick one of the 28, and the probability that we'll pick one of the 7 that we're interested in is going to be, of course, 7 over 28, which is 1/4. You can also ask, what is the probability that the tile we pick will be a double? For example, 1, 1, or 2, 2, and so on up to 6, 6. So again, we need to see how many tiles are doubles, and the number of doubles we again calculated in the previous slide was 7, 0, 0, up to 6, 6, 7 tiles. And the probability that we pick one of the 28 tiles, we get one of the 7 that we're interested in, is going to be 7 over 28, which is 1/4 again. And what is the probability that if we pick a tile, the 2 sides are going to be different? Well, we need to calculate how many tiles have 2 different sides. And there are a couple of ways of doing it. One is to notice that there are 28 tiles, and 7 of them have the same size, the same number on both sides. So the number of tiles that have 2 different sides is going to be 28 minus 7, or 21 over 28, which is 3/4. And we could have arrived at this number 21 in a different way. Again, we had done it before. We need to pick 2 different values out of the 7, which, as we saw in the previous slide, was 7 choose 2, which is 21. So this probability is 3/4. Okay, and so this gives us some ideas about how to calculate probabilities for dominoes. And what we want to do next is look at cards. So just reminding ourselves, a standard deck of cards consists of 52 cards, and they come in 4 suits: clubs, diamonds, hearts, and spades, and in 13 ranks: 2, 3, up to 10, jack, queen, king, and ace. And so the total number of cards we have is 4 times 13, which is 52. Okay, and we can consider picking just one card out of a deck of cards. And if we do that, then to calculate probabilities, because we're picking one card at random, every card is going to be equally likely. So we just need to consider the sample size, the number of possible outcomes, and the outcome is just all 52 cards. So the size of the sample size and the size of the sample space is 52, because there are 52 cards. And each card we're picking equally with equal probability, so it's an equiprobable, again, sample space. And to calculate the probability of each event or outcome, we just need to divide the size of the event by the sample size. So for example, if you ask what's the probability that we're going to pick the Queen of Hearts, we have 52 cards, and the probability we'll pick any specific one, like for example, the Queen of Hearts is 1 over 52. And if we want to see the probability of events, then we can ask, for example, what is the probability that the card that we'll pick will be a heart? So here we're picking 1 out of 52 cards, and we're asking what is the probability that will fall in this set of hearts. And the number of hearts is 13, because there are 13 ranks. So the probability that the card will pick will be a heart is the probability that out of the 52 cards that are there will hit on one of the 13 that are hearts. So it's turned 13 over 52, which is 1/4. And if you ask what is the probability that the card that we'll pick will be a king, well, there are 4 suits. So king comes in 4 different suits. So there are 4 king cards, and the probability that if we pick one card, we'll get a king is the probability that out of the 52 cards that are out there, we happen to pick one of the 4 that we're interested in. So this probability is 4 over 52, which is 1 over 13. And neither of these results, by the way, is surprising, because here, for example, there are 4 suits, and we're asking what is the probability that we'll pick a hearts. That's 1 out of the 4, so this probability is 1/4. And likewise, there are 13 ranks. So if we ask what's the probability we get a king, it's a probability we get 1 out of the 13 ranks, and all of them are equal likely. So the probability we get king is 1 over 13. We can also consider the probability of a face card. So a face card is a card that has a face on it, for example, a jack, a queen, or a king. Those are the only, in fact, face ranks. And of course, they come in 4 different suits. So the probability that we'll pick a face card is the probability that we get jack, queen, or king of any suit. And there are 3 face cards in each suit, but there are 4 suits. The total number of face cards is 3 times 4. And we're interested in probability we pick one of those 12 out of the 52 that we can pick. So that probability is going to be 12 over 52, which is 3 over 13. Okay, and again, not surprising because there are 13 ranks, and 3 of those ranks are face ranks. So the probability that when we pick a random card or a random rank, we'll get one of those 3 is 3 over 13. All right. Now, in general, in games, we don't pick a single card, but we pick a collection of cards that people call a hand. So what we want to do is we want to consider poker hands and their probabilities. So a deck, again, is 52 cards, and a hand in poker consists of 5 cards, 5 random cards from the deck. And the card order the order of the cards does not matter. It's just which cards you have. Okay. So the sample space is the collection of all hands. So if we're going to pick a hand from the deck, we're going to get a hand or collection of 5 cards, and the sample space is the collection of all hands or all 5 cards that we might have. So this is our sample space. And again, notice that we'll get every set of 5 cards, every subset of 5 cards with equal probability. So again, it's an equiprobable set. So we have the same probability of getting this hand as this hand, and so on. Okay. So if we want to calculate probabilities, we just need to find how many different 5-card hands there are, and then we can calculate things. All right. So so to do that, it's quite easy in this case because we have 52 cards, and a hand is a subset of size 5. So how many 5-element subsets are there for a set of size 52? As we know, it's 52 choose 2, and I'm sorry, 52 choose 5, apologize. And the number, when you calculate, comes to 2.6 million, roughly. Okay. So what we're going to do now is we're going to calculate the probability of several hands in poker, and we're going to start with the most rare, or one of the most rare ones, and then go to lesser ones. And the reason we do it in that order is because rare hands, by definition, there are few such hands, and therefore they're easier to count. So smaller sets are easier to count, and we'll start with them. So a straight flush, let's explain these 2 words first. So straight means a consecutive rank sequence. For example, 2, 3, 4, 5, 6. And notice that an ace can precede a 2. For example, ace 2, 3, 4, 5, or it could come at the very end after a king. So we can also have 10, jack, queen, king, ace. That's okay to put the ace there too. Okay, so that's what a straight means, just a consecutive rank sequence. And a flush means that all cards are of the same suit. So for example, all of them are hearts, all of them are diamonds. So together, a straight flush means that you have 5 consecutive cards of the same suit. Okay. So here are a couple of examples. 5, 6, 7, 8, 9 consecutive, and all of them hearts. That's a straight flush. Or 10, jack, queen, king, ace, again consecutive, and all of them spades, is again a straight flush. And to calculate the what we would like to do is calculate the probability that if we pick a random head, we'll get a straight flush. Okay, so to do that, we need to calculate to see how many different hands are straight flushes. Okay, and how many ways can we have a straight flush? Well, we first need to choose the initial rank in the sequence. So we choose the start location of the sequence. Here it's 5, and here it's 10. Now the start location is a number that could be the earliest, the smallest could be is an ace, and can go all the way up to 10. Right, this is the last one that can be. And so we have here 10 different possible start locations or start ranks, and we need to choose one. So it's 10 choose 1. And then once we choose the start location, we also need to choose the suit for all the cards. There's 1 suit, and there are 4 suits. So we need to choose one of them. It's 4 choose 1. So that's the number of ways of choosing the suit. And therefore, by the product rule, if you want, because we chose the start location and then we chose the suit, the total number of straight flush hands is 40. Now, the probability of a straight flush is therefore 40. The probability that we get one of those 40 hands that you're interested in out of the 52 choose 5 possible hands. So that's 40 divided by 52 choose 5. And that's a very small number. It's roughly 1/1000th of 1%. Next, let's consider 4 of a kind. So 4 of a kind hand consists of 4 cards of the same rank and 1 other card. So here is an example. We have 4 kings, 4 cards of the king rank and 1 other card. Here's another example. We have 4 cards that are 4 and then 1 other card, which is a king here. So how many 4 of a kind hands are there? Well, we need to first choose the rank of the 4. Okay, and there are 13 ranks altogether, and we need to choose 1 rank for this 4. So there's 13 choose 1 ways of choosing the rank. And once we did that, we need to, so once we choose the rank, we chose all the cards because we have to take all 4 cards of that rank, and we just need to pick the 1 remaining card. Now we chose 4 cards, we cannot choose one of them again, so the number of cards remaining is 52 minus 4, and we need to pick one of them. Any of them will be fine. So we have times 48, which is 52 minus 4. Choose 1 for the other card, and the total number is 624. And therefore the probability of choosing 4 of a kind is 624 divided by 52, choose 5. And that is a little higher than what we had before, but it's roughly 2% of 1%. Right. Now let's go to more likely hand. Full house. A full house consists of 3 cards of 1 rank and 2 cards of another rank. For example, 3 aces and 2 kings, like here, or 3 threes and 2 queens, so 3 cards that are of the 3 rank and 2 cards of the queen rank. So that's a full house. And to see how many full house hands are there, notice that we need to choose the rank for the triple and the rank for the pair. So how many ways can we do it? It's 13 to the second falling power. So recall that this denotes 13 to the second falling power, in other words, 13 times 12. That's because we have 13 ways to pick the rank of the triple. And once we pick the rank of the triple, we need to pick the rank of the pair. We have 12 ways of doing that. And then once we pick the rank of the triple and the rank of the pair, we need to pick the 3 cards, the triple, and we have 4 possibilities for the triple. For example, here there are 4 aces that we could have chosen from, but we need to choose 3 of them. So there are 4 choose 3 ways of picking which 3 cards are in the hand from the triple, and then we need to consider the hand. Again, there are 4 cards that we can choose from that rank of the double, and we need to put 2 of those cards. So there are 4 choose 2 ways of picking that, and so this number, and the product is just by the product rule, is just the total number of hands that we can have, right? We need to specify the rank of the triple, the rank of the pair, and then which triple we took out of the 4, and then which pair we took out of the 4 of the rank of the pair. Okay, and that number is 3,744, and the probability is roughly 0.14%. Okay, now a flush. Remember that we talked about this before. A flush is a hand where all cards have the same suit. For example, here they're all hearts. Okay, and we have already considered straight flushes where we have a flush, all of them of the same suit, but in addition they're all consecutive. For example, 2, 3, 4, 5, and 6. So what we would like to consider now are flushes that are 5 non-consecutive cards of the same suit. Okay, and the reason they're not consecutive is because we want to distinguish from a straight flush. So if they were of the same suit and consecutive, there would be a straight flush, and if they're of the same suit and non-consecutive, then we have the flush that we're considering now. Okay, so how many flush hands are there? Well, we need to pick the suit. For example, hearts here, and there are 4 suits. We need to pick one. There are 4 choose 1 possibilities. And then once we pick the suit, we need to pick the 5 cards of all the cards of the same suit. Remember, there are 13 cards of any given suit, and we need to pick 5 of them. So that's 13 choose 5. But the 13 choose 5 also includes the consecutive hands. So we need to subtract that. So we need to consider 13 choose 5 minus the number of consecutive hands of the given suit that we had chosen. So 13 choose 5 is the number of ways to select 5 cards from a suit. And if you remember, we said that for any given suit, there are 10 hands of consecutive cards depending on where they start. You can start with ace, 2, 3, 4, 5, all the way up to 10, jack, queen, king, and ace. So there are going to be 10 consecutive cards that we're not interested in. So we're subtracting 13 choose 5. These are all ways of picking 5 cards minus the 10 consecutive ones that we don't count here. So we have 4 ways of picking the suit times this number of picking non-consecutive cards from that suit, and that product is roughly 5,000, and the probability is roughly 0.2%. And the last hand that we're going to do now is straight, and you can and a straight consists of 5 consecutive cards, as we had actually said before again. So straight means you have 5 consecutive cards. But again, if the straight was again a flush, then we would have had a straight flush. And we want to consider just straights that are not flushes. So we're looking at 5 consecutive cards that are not all of the same suit. Okay. So here is an example. We have 10, jack, queen, king, and ace. They are consecutive, but they're not all of the same suit. They're not all hearts, they're not all spades, and so on. Okay, so how many are there? So, and again, remember that in a straight, an ace can either precede the 2 or succeed the king. So like here, it goes after the king. We can count it both ways. And so how many straight hands are there? Well, we need to pick the initial location, the start location, and that's a rank that starts from ace up to 10, as we had seen before. So that's the beginning. Here it's 10. And then once we pick this, we need to pick the 5 cards. So we know we're going to have a card of 10, a card of jack, and a queen, and a king, and an ace. But we have many possibilities of picking those. And in particular, we have 4 ways of picking the 10, because there are 4 suits, and 4 ways of picking the jack, and so on. So we have 4 to the 5 ways of picking those cards. But remember that we want them not to be all of the same suit, so we need to subtract. So these are 4 to the 5 is the number of ways of picking a suit for each card. But we are not interested in hands where all of them are of the same suit. Luckily, there are very few hands where all of them are of the same suit. If the cards are 10 up to ace, they're either 10, 11, sorry, 10, jack, queen, king, and ace, all of hearts, and the same thing of diamonds and spades. And of clubs. So there are 4 choose 1 hands that are flush, that are the same suit, corresponding to just picking the 1 suit. So we need to subtract that. So we have 10 to choose 1 ways of picking the start location, and then we need to count the number of ways of picking the 5 cards so that they're not going to be all of the same suit. So we have 4 to the 5. That's the 4 possibilities of picking each rank. So 4 to the 5, but we need to subtract the 4 hands that are all of the same suit. So that's this number here, and multiply, get a little over 10,000, and the probability is roughly 0.4%. Okay, so in essentially this way, you can calculate the probability of all other poker hands. There are just about 3 left. For example, full house and so on. The calculation is going to be exactly the same, so I'm not going to do it. But you can. I recommend that you calculate those numbers. And also, in the notebook, we have simulations for probabilities of several poker hands. So you can run those simulations and see that for the hands that we had evaluated now, we get the same probability by simulation. And you can also modify the program and find the probabilities probabilistically by simulation for other hands. Okay. So with that, we're done talking about games of chance. And so we have continued discussing uniform probability spaces, where calculating the probabilities of outcomes and events is relatively simple, because we just need to divide the size of the event by the size of the sample space. And today, on this lecture, we talked about several games, a couple of games of chance. And what we want to do next is move from uniform probability spaces to general probability spaces. Talk about it next time. See you then.